We left off our discussion of Chapter 17 looking at the two different kinds of models we get from Bernoulli trials. The first was geometric, and we said we had seen that in Chapter 15. And the second is binomial, and that's what we're going to take a look at today. These are out of kinds of questions. We have a certain number of successes and a set number of trials. So here's our question. A new sales gimmick has 30% of M&Ms covered with speckles. These groovy candies are mixed randomly with the normal candies as they are put into the bags for distribution and sale. So you buy a bag, and suppose you pull out just 5 candies. What's the probability 2 are speckled? Okay, we get 2 out of 5. Okay, I'm looking for the probability of 2 speckled out of 5. This is a binomial question, right? I have this out of. I have a set number of trials. I'm only choosing 5 M&Ms. It's set. And I'm asking about a number of successes. So that's what makes this binomial. It is still Bernoulli. So remember, Bernoulli could make 2 things. So it is still Bernoulli. Think about, we have 2 outcomes. Either an M&M is speckled or it's not. There's a fixed probability. Well, 30% chance of getting a speckled M&M. And our trials are independent simply because we have less than 10% of all M&Ms. So as we're thinking about this question, probability of selecting 2 speckled M&Ms out of 5, some of you are probably going to think, well, let's do it this way, where you get a speckled M&M and a speckled M&M and one that's not speckled, and then one that's not speckled, and then one that's not speckled. All right, let's take just a moment and crank out a number for that. Well, probability for speckled is 0.3. So we're going to have 0.3 times 0.3. Trying to space these out pretty far for us. Times, this is 0.7 for not speckled, times 0.7 for not speckled, times 0.7. So if we type that all in our calculator, we get 0.03087. Now that's a great start, but that's not actually the answer to this question. And I want to point out why. You're not going to like this, but I'm going to do it. What we set up here, what we really wrote down is that the first and second M&Ms you pick are speckled. But I didn't say it had to be the first and second that are speckled. It could be any 2. So we could have done it this way. Not speckled, and not speckled, and not speckled. And it could have been the last 2 that were speckled. Or maybe it was the first one that's speckled, and the last one. Or maybe I could alternate them. Hopefully you're getting the idea here. There are lots of different ways I can arrange 2 speckled out of 5. Now, I know some of you are protesting already. You're saying, but guess what? This answer, because multiplication you can do in any order, I'm still going to get the same number. That's right. Every time I arrange it, I'm going to get the same number. That's true. The problem is, all of these arrangements give me what I want. So I could do it this way, or this way, or this way. Okay. Or means add. So I would have to add all of these together. Okay. Because the order doesn't matter, I need to acknowledge that there are a lot of possibilities. I could get it this way, or this way, okay? Or means add. So then what I need to know is, well, how far does it go? How many different arrangements are there? So I can add these all together successfully. Now, just so that we don't get horribly bored, I'll just tell you there are actually 10 different ways to order 2 speckled M&Ms out of 5. So I would need to add 0.03087 10 times. Okay, well that's 10 times 0.03087. So that gives me 0.3087. So I have about a 30% chance of getting 2 speckled M&Ms out of 5. The important thing that I want you to notice here is that we had multiple ways to organize this. So that means we're going to need a shortcut, because I don't know about you, but I don't want to have to figure out what all the different ways are so that I can count them and realize there are 10. There's got to be a shortcut. As a matter of fact, there is. That shortcut comes from understanding the binomial model. All right, in our binomial model, just want to point out, this is how we write down if somebody asks about the binomial model. Remember the normal model, we would write n, and then there were kind of 2 important things to know, the mean and the standard deviation. So this is the same idea for binomial. We need to know the number of trials, that's n. And we need to know p. Hopefully in your mind, that's your probability. And it's the probability of success. Remember, success doesn't have to be something happy. It's just whatever we're looking for. And on your AP formula page, you will be given these formulas. So if anybody asks you about calculating a mean, right, mu, mean, for a binomial, you do that by taking n times p. If anybody asks you about a standard deviation for a binomial, okay, standard deviation, you do that by taking the square root of n times p, and the AP formula page writes it this way, 1 minus p. Your book writes it this way, q. Remember, q is 1 minus p. So just keep in mind, your book is going to write it one way, your AP formula page will write it a different way. It means the same thing. All right, and last and most importantly, this is also going to be on your formula page. Here's how we calculate the probability for a binomial. Pretty cool. If I want to know the probability that I get a certain number of trials, a certain number of successes, so this is how many successes, I'm going to do this interesting thing. This is not a fraction, and it should actually look a little bit more like the letters right on top of each other. We read this as n choose k. N choose k. This cool thing right here counts how many different ways to arrange something. So this is how I got that number 10 on the last example. It's just a cool mathematical thing. It's called a combination that will calculate that for you. Then we do p, the probability of success, times how many of those we're looking for. And then we have our 1 minus p, or q if you prefer. And we're going to take the leftovers, the number of trials minus how many successes we should see. So let's go ahead and use that formula in our story problem. Okay. So I wanted to know the probability that my binomial gets 2 speckled M&Ms. I'm going to do that by taking n, that's the number of trials, the number of M&Ms I have is 5. Choose k. K is how many I wanted. I wanted 2 speckled M&Ms. P, what's the probability of speckles? It was 0.3. 0.3 to the k. Again, that k, that is this one right here. 2 speckled M&Ms. Then I have 1 minus p. Well, 1 minus 0.3, that's 0.7. And it's to the n minus k power. Oh my goodness. Well, remember, n was 5. I had 5 M&Ms. I wanted 2 of them to be speckled. That means 3 of them can be just plain old regular M&Ms. All right. So hopefully you're recognizing this part we wrote out. Right, that was here. We had 0.3 twice and 0.7 3 different times. Okay, same thing we have here. And then this, 5 choose 2, gives us the number 10. So how many different ways can we arrange it? All right, so you're probably wondering, how do I actually type that in on my calculator? Well, you need to be able to write it down in the formula, but there's a shortcut. You don't even have to type in this much on your calculator. There's actually a binomial place on your calculator, and it's called Binomial Pdf. And in class, we'll talk about the difference between the PDF and the CDF. And if you tell your calculator 3 things, it will calculate the binomial probability for you. So you need to be able to write it this way. So you should be able to write 5 choose 2, 0.3 to the 2 times 0.7 to the 3 equals, then you're just going to copy the answer down from your calculator. But you'll type it in this way. I remember NPX because nobody plays the xylophone. And remember, N is the number of trials. So when we type this in our calculator, N is the number of trials. There are 5 M and N's. P is the probability we get a speckled one. And X is like K in the formula. It's how many we're looking for. All right, so I want to show you where to find that. We're going to go to the distributions, same place we've been finding our normals. And if I just scroll around, eventually I'm going to see something that looks happy. Binomial Pdf. There is a binomial CDF. We're not going to talk about that one right now. So pick binomial Pdf. So we're going to type in right what I wrote on the screen. N, comma, P, comma, X. And 0.3087. So I just need to be able to copy that down. 0.3087. By the way, in case you wondered, that is actually the answer we came up with. But I think that was a whole lot easier. All right, so just one more. An Olympic archer is able to hit the bullseye 80% of the time. Assume each shot is independent of the others. The reason that's mentioned is so that we know these are actually Bernoulli trials. There are 2 possible outcomes. You either get a bullseye or you don't. The probability of getting a bullseye is fixed to 80%, and we're assuming each shot is independent. So since it's Bernoulli, we can go ahead and talk about binomial. If she shoots 6 arrows, what's the probability she gets exactly 4 bullseyes? So 6 arrows. We want 4 bullseyes. That's 4 out of 6. That's how I know it's binomial. So I copied down the formula here so that we can do it again. N, the number of trials. How many times is she shooting altogether? That would be 6. K, how many successes are we looking for? We are looking for 4 bullseyes. P, what's the probability of that success? What's the probability of getting a bullseye? It is 0.8 to the K power. Hopefully you're noticing there's a K here and a K here, so those numbers should be the same. 1 minus P, that's going to be 0.2 to the N minus K. Well, look here, here's an N, here's a K. So it's 6 minus 4, that's 2. Go ahead and type this in your calculator and see what you get as the final answer.